Hello. In this video, I'll define what is meant by an automorphism of a graph. We'll also define the automorphism group of a graph, and we'll take a look at a few examples. So first off, an automorphism of a graph is just an isomorphism from G to itself. So that is a mapping from the vertex set of G to the vertex set of G that preserves edges and preserves non-edges. So let's just take a look at an example. Here is G1, and let's just find all the possible automorphisms from G1 to G1. So let me maybe put this here, all automorphisms. So one important thing to note is that no matter what graph you're looking at, there's always the identity automorphism. That is the automorphism that's just the identity on the vertex set that sends every vertex to itself. So we'll call it epsilon here is the identity automorphism. And so this would send U gets mapped to U, V gets mapped to V, W gets mapped to W, X gets mapped to X, right? You get the idea. Y, oops, sorry, Y also gets mapped to Y. Every vertex is mapped to itself. That's the identity. And since I haven't changed any of the labels, all the adjacencies are preserved and all the non-adjacencies are preserved. So that one you get for free. Every graph has an identity automorphism on it. But this graph has another automorphism on it. So one way I sort of like to think about automorphisms is if you want to keep the graph to look exactly how it is, but sort of relabel it. So what I mean by that is I can move around vertices in this graph, but I need to place a vertex where there used to be a vertex. So like I can move U to Y, but then I'll have to move, in this case I'd have to move Y to U. I'd have to place another vertex there at U. I don't always have to swap vertices like that, but what I'm talking about is moving the vertices around so they land on the place where another vertex used to meet, where another vertex used to be. You can check that that's an automorphism if, when you do that, all of the edges that come along when you move the vertices land on the edges of the graph, and all of the non-edges land on non-edges. So as I mentioned before, right, we can send U to Y. So let's start our automorphism off like that. I'm going to call this alpha, this automorphism alpha. I'm going to map U to Y. So one way I know that I need to send U to Y, any automorphism is going to have to involve either sending U to U or sending U to Y, because these are our only two vertices of degree 1. And remember, an isomorphism has to preserve the degree of the vertex. So I can send U to Y. Delete the arrow because I don't want this to appear like a digraph. So I swap that I send U to Y. And then since Y, right, U and Y are the only vertices of degree 1, Y also has to be sent to U. Okay, well now that I've sent U to Y and XY was adjacent, or rather UV was adjacent originally, that means I need to swap V with X. So V needs to be sent with X. And since YX were originally adjacent, and I sent Y to U, that means X needs to be sent to V. So X goes to V. And then finally, W, it's the only vertex of degree 2. So any automorphism has to leave W fixed. It's a fixed point. So W gets sent to W. Notice that once I decided to send U to Y, everything else was determined. I didn't really have any choices in the other, what vertices I sent to what other vertices. Everything was predetermined past that point. And so we can actually conclude here that these are all of the automorphisms of G1, right? The two vertices of degree 1 must either be fixed, as in the case of the identity, I send U to U and Y to Y, or they're swapped, where I send U to Y and Y to U, and then the rest was determined. There are no choices after this point. So these are the only two automorphisms. So the set of automorphisms is just epsilon and alpha. All right, so now to get into some algebra, this is not just a set. So the collection of automorphisms is not just a set. It actually has more structure than that because I can compose automorphisms with each other, right? Automorphisms are functions, and so we can compose two functions with each other. So let me say, can compose any two automorphisms. For example, I can do epsilon, or yeah, I can perform epsilon, do that function on the vertex set of G1, and then I can apply alpha to that. And what'll happen? Well, I'll send u to u, and then I'll send u to y. And so u gets sent to y. I'll send v to v, and then v gets sent to x, so v gets sent to x. Well, as you can see, since epsilon is the identity automorphism, that this is really just going to be alpha. All right, well, what about composing? So that was epsilon and alpha together, but what about alpha composed with itself? So alpha composed with alpha. So first, in this, I would send u to y, and then I would do alpha again, so I'd send y to u. So u gets sent to u. Let's see. So u gets sent to u. I would send y to u, and then u gets sent to y, so y gets sent to y. And you can check for each one of these, right? V gets sent to x, x gets sent to v. W gets sent to w, w gets sent to w. You can check that this actually gives the identity automorphism when I compose alpha with itself. Of course, we can do epsilon with itself, but that's going to just give us the identity. And so really, so I can actually put these in a chart, in a Cayley diagram. So I have epsilon and I have alpha, and I want to know how these interact with each other. These are my two. So epsilon with epsilon gives me epsilon, alpha with epsilon gives me alpha, alpha with epsilon gives me alpha, and epsilon with, or alpha and alpha give me epsilon. So this is a diagram for how these elements interact with each other in this under composition. So one thing to note here is that alpha, every element of this set has an inverse. In particular, the inverse of alpha is itself. It's epsilon, right? Alpha with alpha gives us epsilon. So that means alpha, right? This means alpha is alpha inverse. And of course, epsilon is the identity. So this is going to be true in general, that given the automorphisms of a graph, so maybe, yeah, I'll write this down. So given, let me actually type it. Sorry, hold up one second. So given the automorphisms of a graph, the composition of any two give us another automorphism. So this is closure. There is an identity automorphism, and that's just the identity function. And what do we have? Every automorphism has an inverse automorphism. So together, these tell us that the set of automorphisms under composition is a group, right? It's the algebraic structure that is a group. So if you haven't had a abstract algebra class or modern algebra class, you might be unfamiliar with what a group is, but this is essentially the idea of a group, that under the operation, any two elements under that operation, again, give you an element of the group. For every element, there's an inverse element, and there exists this identity element. So here's the idea of a group. So the automorphism group of a graph, it's the set of all automorphisms of the graph under composition. So given a graph, we call this the automorphism group. So given a graph, let's call it G. We call this the automorphism group of G, and we denote this by aut, A-U-T, of G. So it's the set of these automorphisms under composition. All right. So that's an automorphism group. So let's take a look at another example. All right, how about G2 here? Question, given any graph, can be, what is the automorphism group of the graph? So we'll say automorphism group of G2. It's what? All right, well, we always get the identity automorphism. So we'll call it epsilon here again, and I'll just say the identity. And then let's see, are there any more automorphisms? All right, well, I claim there aren't any. And here's my argument. You might have a different argument, but this one works. So Y is the only element of degree 2 in this graph. Sorry, Y and W are the only vertices of degree 2. And W and Y are only two of degree 2. So either W gets sent to itself and Y gets sent to itself, or we do W gets sent to Y and Y gets sent to W. So if W gets sent to W and Y gets sent to Y, it's pretty clear that then we need Z to get sent to Z, X to get sent to X, V to get sent to V, and U to get sent to U. That is, the rest of it will be determined and will lead to the identity automorphism. So if this happens, we can pretty quickly see that we'll get the identity automorphism. Now, what if W gets sent to Y and Y gets sent to W? If I swap those two, well, that's going to be an issue because Y is adjacent to a vertex of degree 1. However, W is not adjacent to a vertex of degree 1. And so this does not lead to any automorphism. Right? Remember, we have to preserve adjacencies. So that is, if Y is a vertex adjacent to another vertex of degree 1, it has to get sent to a vertex adjacent to a vertex of degree 1. So this tells us that epsilon is the only identity. And so what is automorphism of G2? Well, it is, it's the identity group. It's Z1. Yeah, so we can label this Z1. It's the trivial group. Integers modulo 1. That's another way to think of the trivial group. I'm going to journey back here for a second because we didn't actually determine, if you're familiar with some basic group theory, you know that we can classify small, or really any finite group. So we can classify this. So automorphism of G1 here consisted of the identity element and this alpha. And we had alpha squared was equal to epsilon. And so this is very similar to, or it's actually exactly the same. It's isomorphic to the integers modulo 2. So that is, I have the elements 0 and 1 under addition. This is Z2 under addition. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1, and 1 plus 1 is 2. Modulo 2 is 0. And so that's exactly the same as here. We can find a group isomorphism from integers modulo 2 to the automorphisms of, so this is automorphisms of G1. Right here we would send epsilon would get mapped to 0, and alpha would get sent to 1. So this is really the same as the integers modulo 2. It's the same algebraic structure as the integers modulo 2. Just like with G2, there was really no automorphisms besides the identity, and so this was the trivial group. It's just basically 0 by itself. All right. So last one for this video, let's take a look at a cycle. Let's take a look at C4. And let's find the automorphism group of C4. All right. Let's see. So we always get epsilon. Epsilon always comes for free. That's our identity. All right, so let's build another automorphism here. I'm going to call this one, what do I want to call this one? I'll call this one about alpha, alpha 2. And in alpha 2, what I'll do, actually, before I do this, I'm going to give you another way to express these automorphisms. So here I'm expressing my automorphisms by just giving you the mappings from vertex set to vertex set, like I did with G1. But there's another way I can express these automorphisms. I can use cycle notation. So here with alpha, so let's take maybe alpha and go down here. So right, so U gets sent to Y. And so I'm going to write this in the following way. U gets sent to Y is what that means. And then Y gets sent to U. So I'm going to close off that cycle. So this cycle, this 2 cycle here means U gets sent to Y and Y gets sent to U. And now we have V gets sent to X and X gets sent to V. So that's V gets sent to X, and X gets sent to V. Now, one thing you can do for this cycle notation is you can, if you want, you can just put W by itself to say W gets sent to W, but oftentimes this is left out, that you only picture 2 cycles or above. So this is another way to express alpha. So let's see in C4, how I can represent this. So I'll do it first by telling you the mappings, and then I will express it with a cycle notation. So one thing I can do is everything's degree 2, so I could send U to V. So maybe I'll do U gets sent to V. And then, so if U gets sent to V, well, U and V were adjacent, and V was adjacent to W, so it appears now I need to have U sent to W. So I'll send U to V, I'll send V to W, I'll send W to X, and I'll send X to U. In other words, what I'm doing is I'm rotating the 4 cycle by 90 degrees. So another way to express alpha 2 here is with a cycle. The element U is being sent to V, V is being sent to W, W is being sent to X, and then X is coming back around to U. So that's alpha 2. Now, what's alpha 1, you might ask? Well, I'm using the book's notation here. Alpha 1, they are talking about the trivial rotation, so the rotation by 0 degrees, and so that's the same as the identity. So they're calling that one alpha 1. I think it's a little bit silly. So alpha 2 is this. Let's see, what else could we do? we could do a rotation by 180 degrees. So in this case, U would get sent to W, V would get sent to X, W would get sent to U, and X would get sent to V. So that was U gets sent to W, and then W gets sent back to U, V gets sent to X, and X gets sent back to V. Let's see. Sorry, wait, give me 1 second. I may have misinterpreted something. Sorry, yes, I did misinterpret something. They're not calling alpha 1 W. No, this makes a lot more sense to me now. Sorry, I had to reread. Upon realizing it wasn't making any sense. Alpha 1 is this rotation by 90 degrees. Alpha 2 is our rotation by 180 degrees. And then alpha 3 will be our rotation either counterclockwise by 90 degrees or clockwise by 270 degrees. So alpha 3 will be, so U will get sent to X, X will get sent to W, W will get sent to V. We'll go around the other way. So that's U gets sent to X, X gets sent to W, W gets sent to V, and then V gets sent back to U. So right now we have 4 automorphisms here. However, so if I send, there's other ones, right? If I send U to W, so let's maybe start another one here. We're going to call this one theta. Call it theta 1. If I send U to W, like we do in alpha 2, that rotation by 180 degrees, U gets sent to W, but I don't have to send V to X. I don't have to rotate the whole thing, right? If U gets sent to W, I could also send V just to itself. V gets sent to V, and I can send X gets sent to X, and then W will get sent to U. Right? So U is adjacent to V and X, and W is adjacent to V and X. So I can send U to W and keep V and X the same, and I haven't changed the adjacencies at all. So that'll still preserve adjacencies. So that is what I just did was a reflection about this diagonal line that I just drew. That's alpha 1. So you might also wonder, well, why don't I do a reflection across this diagonal line? So, oh yeah, here, let me do the cycle notation for that. Theta 1 was U gets sent to W, and W gets sent back to U. Right, so I could also do it across this diagonal line, and I'll call this one alpha 2, or theta 2. Here, V will get sent to X, and I'll leave U and W fixed. Okay, but there's some other reflections here as well. I could reflect across this horizontal line. I'm going to call this one, yeah, I want to, so maybe think about, yeah, the vertical line as well. I could reflect across the vertical line or the horizontal line. If I reflect across the vertical, send U to V and V to U, we'll call this one theta 3. This will be U gets sent to V, V gets sent back to U, and then X gets sent to W, and W gets sent back to X. And then if we reflect across the horizontal line, this would be U to X, X back to U, and then V to W, and W back to V. And so we get this set. So that was identity, alpha 1, alpha 2, alpha 3. We had theta 1, theta 2, theta 3, and theta 4. And this ends up being all of the automorphisms. One way we can check, well, we can keep thinking about, are there other ways to send these elements around? And then what we can do is we can look at compositions of these automorphisms with each other. And we'll notice some things, that all of these reflections, so theta 1, theta 2, theta 3, and theta 4, each one of these composed with itself gives us the identity. Let's see, alpha 1, if I square alpha 1, if I compose it with itself, I end up with alpha 2. If I do alpha 1 cubed, I'll end up with alpha 3. And if I do alpha 1 to the 4th, I'll end up with the identity. So what this actually establishes is that this identity, alpha 1, alpha 2, alpha 3, this is a subgroup of the automorphism group. And then I can also compose these rotations with the reflections. If we do something like alpha 1 composed with, I'll just do 1 for an example, composed with theta 1, we should end up with a different automorphism. So here we would do theta 1 first. So I would send u to w, and then alpha 1 sends w to x. So that means u would get sent to x. Okay, u gets sent to w gets sent to x. Where does x go? Well, by theta 1, x gets sent to itself, and then x gets sent to u by alpha 1. So x would go back to u. All right, cool. How about w? What happens with w? So theta 1, that's happening first. W gets sent to u, and then u gets sent to v. So w gets sent to v, and then v will have to be sent back to w, and we can check that, make sure we did it right. V is fixed by theta 1, and then v gets sent to w by alpha 1. So alpha 1, theta 1 composed with alpha 1 gives us this, uxwv, which is theta 4. Sorry, that's not theta. I've been saying theta. This is phi. Sorry, I think the whole time I've been saying theta. This is phi, not theta. Anyway, you can check all of these, all of the compositions. You could do one of these Cayley diagrams if you want to do this completely, like this one. What you'll see is, yeah, this is really the group, and this is a known group. This is a dihedral group. So this is isomorphic to, what does our book use? D4, D8. So this is D4, the dihedral group of order 8. And actually, this is going to be true for all cycles, that cycles are going to end up being the dihedral group. So what you'll see is a subgroup of rotations, and then twice as many as that of these reflections. So you can try this out now for a homework problem for the automorphism group of C5 would be a good one to try out next. Okay, that's it for this. In the next video, we're going to look at the automorphism group of complete graphs, and then some facts about automorphism groups. See you there.